Okay, for our last chapter, our last section in our college algebra skill sheets, we're going to talk about section 9.7, which is probability. And this is the introduction to the big idea that goes on in statistics. So we're just going to go through this and have an introduction to sample spaces and computing basic probabilities. Things get much more involved when you actually get into statistics, and you talk about all of the different types of probabilities that you can compute. But we're just going to look at some classical probability problems right now, some theoretical probabilities. And I might mention to you the difference between theoretical and empirical as we get on down here. But all of these that we're going to talk about today are theoretical. So, all right, many events in life are inherently uncertain. Will it snow tomorrow? Am I going to get an A in this course? None of these questions can be answered with certainty. However, we may say that some are unlikely and others are more likely. The probability of an event is a description of how likely it is that the event will happen. So you've probably seen a forecast, which is something that has to do with probability that says what % chance of precipitation you have in the forecast for the next day. And you look at that and it helps you decide whether you think there's a good chance that it's going to rain or snow, or if there is not a good chance that it's going to rain or snow, and how you should maybe plan your outdoor activities for a particular day, right? So probability is a number between 0 and 1, that is between 0% and 100%. Probabilities closer to 100% are very likely to occur, and probabilities closer to 0% are very unlikely to occur. A probability of 0% means that the event is impossible, and a probability of 100% means that the event will certainly occur. So a probability model, which we talked about a little bit in the last video, and I called it a probability distribution function, or a PDF, is a mathematical description of an experiment listing all the possible outcomes and their associated probabilities. Lots of times we do that with a chart that we're not going to do today, but I might make one of those just so you get to see it. It is defined by its sample space, events within the sample space, and probabilities associated with each event. The sample space S for a probability model or probability distribution function is the set of all possible outcomes. For example, the sample space for rolling a die is the set S equals 1, 2, 3, 4, 5, 6. Those are all the possible outcomes you can get from rolling a 6-sided die. This notation is referred to as roster notation when I put it in set brackets like this and list all of the possible options. An event A is a subset of the sample space S, meaning that it contains some or all of the elements of set S. For example, the event rolling an even number is the subset A equals 2, 4, 6. So 2, 4, and 6 are the only even numbers on the die. To calculate the probability of an event, we divide the number of possible outcomes of the event, that means these favorable outcomes here, by the total number of possible outcomes of the sample space. That would be the number of possibilities here. So for instance, they're going to calculate the probability of rolling an even number on a die. There's 3 even numbers in set A here, and there's 6 total numbers in set S there, and 3 divided by 6 is going to be 1/2. We usually leave it as a fraction, but we could write that as a decimal, as an exact answer, 0.5. We could also write it as 50%. So we could express it in any of those ways, but fractions are usually best so that we don't have to round and approximate any decimals. These are exact answers. So we like to leave our fractions because we want all the fractions to add together to give us 100%. That's one of the things about a probability distribution function, is that because we have all the outcomes possible from set S represented, that all the probabilities have to add together to be 100%. And all those probabilities have to be between 0 and 1. All right, describe in set notation the sample space of tossing a coin. We're going to assume that this is a coin that has heads and tails, right? So I'm going to here. So my sample space is going to be H or T. That's how I'm going to represent it for heads or tails. Find the probability that the coin lands on heads. I'm going to use a chart here just so you can see what I call X and P of X. So here's heads, here's tails. There's 1 heads on the coin out of 2 sides. There's 1 tails on the coin out of 2 sides. This is how I represent my probability distribution function. And they wanted us to find this probability here, the probability that it lands on heads. So P of heads is exactly equal to 1/2. Let's describe in set notation the event of rolling an odd number. So again, let me just go ahead and make this chart. We have the options 1, 2, 3, 4, 5, and 6. Each of these is 1 out of 6 sides on the die. They're not always going to be equally distributed like this, but for most of the problems that we're going to do today, it's going to be 1 divided by the number of things in the sample size or in the sample space, so that each of these is equally distributed. So the odd numbers are 1, 3, 5. So I've got 3 of them. So the probability of an odd is going to be 1/6 plus 1/6 plus another 1/6, just like we did with ORs a couple worksheets ago. So that's 3 out of 6 or 1/2. Now I'm not going to do a chart like this for drawing a card. Instead, I've got a picture already down below of that, and that is right here. So if you've not seen a deck of cards, if you're not familiar with it, that there are going to be 4 suits. This suit here is called clubs. This suit here is called diamonds. This suit here is called hearts. And this suit here is called spades. These are called aces. And then you've got 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, 10s. Those are pretty obvious because they're numerical. This J stands for a jack. This is a queen. And this is a king. So these 3 cards here are called face cards. And I think you can see why they're called face cards, because they've got faces on them. The aces, as you can see on the card itself, have a value of 1, though in many games they're actually considered to be the highest card that's actually above a king. So we'll come back and we'll look now at what the probability of getting an ace is. So there are 1, 2, 3, 4 aces out of, and there are 4 times 13. 1 through 10 is 10, and then 3 face cards is 13. So 4 times 13, there's 52 cards in a standard deck. Sometimes we play games where we're not playing with a full deck of cards. That's an idiom sometimes to say something about somebody, but for instance, the game Euchre that I like to play only uses the cards 9, 10, Jack, Queen, King, and Ace. So 6 cards from each suit. There's 24 cards in the Euchre deck. So, but if you're going to play poker or spades or hearts or rummy or any of those sorts of things, you're going to be playing here with a full deck. Blackjack is another one. We're not going to talk about probabilities of getting certain hands or anything in any of those games. That's too complicated. We're just going to talk about the pick a card, any card type, magic trick, and what's the probability of drawing an ace. So there is an ace of spades. There's an ace of hearts, or of diamonds, excuse me. I'm going on the way that it's listed. An ace of hearts, ace of clubs. Okay, you might have gotten those in the wrong order. I think this was supposed to be, clubs was supposed to be first and spades last. And so the probability of drawing an ace is going to be 4 out of 52. And I already told you that 52 is 4 times 13. So we're going to cancel those 4s. So we're going to be left with 1 out of 13. So again, they went ahead and did all the arithmetic here for you. I went and did it above and wrote it out. But there's nothing new here. This is the answers to all of those previous problems where we had 1/2 for the probability of heads. The probability is 1/2 to get an odd number when rolling a die, and the probability of getting an ace or any other denomination of card in a standard deck of cards is 1 out of 13. The probability of getting any suit, a card from any suit, is going to be 1 out of 4 because there's 4 suits, but there's 13 denominations of cards, ace through king, and so the probability is 1 out of 13. All right, we're going to look at something now where the probabilities aren't all split up equally, and we're going to use a spinner to represent this, but we know all the possible outcomes and everything has an equal, it's equally divided. The area of each section is the same. We don't have bigger and smaller sections here. So describe the sample space. So S is going to be the set of red, yellow, blue. Okay, so I'm going to do X, P of X, red, yellow, blue. Let's do something a little different this time. I'm going to do, let's pretend that I don't know how many are there right now, and I'm just going to do my frequencies. So how many reds are there? There's 4 reds, there's 3 yellows, and there's 1 blue, which means that my N is my sum of all of my frequencies is 8. So my probability is F divided by N. So that's 4 divided by 8 is 1/2. 3 divided by 8 is 3 divided by 8, and 1 divided by 8 is 1/8. So if I would add all those probabilities together, 4/8 plus 3/8 plus 1/8 is 8/8, which is 100%. So describe the Sample space and set notation, we did that for part A. Find the probability the dial stops on a yellow slice. So we did that. That's 3 out of 8. Find the probability the dial stops on a red slice. We did that. That's 1/2. Find the probability the dial stops on a blue slice. We did that. That's 1 out of 8. All right. Now we've got some stuff that has to do with cards. So I'm going to let you look at this diagram while we answer these questions. So draw a diagram. They wanted you to draw this. I went ahead and put a picture in there into the PDF. So we've got 2 suits that are black and 2 suits that are red. And so describe in set notation the event of drawing a king. P of, so we talked about this earlier about set K, I'll call it, is, so there's a king of clubs, king of diamonds. Here, I'm just going to use symbols. I'm not really great at drawing these symbols, but I'm going to try and draw them anyways. So there's the king of clubs. There's the king of diamonds. There's the king of hearts. And there's the, this is the one I'm really bad at drawing, king of spades. Okay, so we'll call this set A. Find the probability of drawing a king is going to be that those 4 cards out of the 52 cards total is going to be 1 out of 13. A and B. C, find the probability of drawing a club. So set B is equal to all of these cards up here, all 13 of them. I'm not going to list them all out, but ace of clubs all the way out through the king of clubs. And so the probability of event B is going to be 13 out of 52, which is 1 out of 4. Drawing a red 6. So red 6, there's the 6 of diamonds or 6 of hearts. So diamond 6 or heart 6. Oops. So it's just going to be event C. Probability of C is going to be 2 out of 52 is going to be 1 out of 26. Okay, so that's how you work that out with these probabilities. I didn't do anything here where I didn't have replacement. But remember when we talked about ands and ors and things like that, if I draw multiple cards out of the deck of cards and I don't replace them, I have to change the probability of each card. So if I say the probability of pulling a 2, then a 5. So the probability of getting a 2 first is 1 out of 13 times the probability of getting a 5. There's going to be 4 5s left because I pulled a 2 already, but there's only going to be 51 cards left in the deck. So I may want to change this to make it be 4 out of 52 times 4 out of 51 is going to be, oh yeah, that is going to cancel like that. is going to be 4 out of, and then 13 times 51 is a big number. $663. Okay, so that's just an example of what we call a dependent probability. Instead of independent trials here, if the available cards to choose from have changed, or the available number of marbles have changed, or people, or whatever, and you don't have the same choices every single time because I didn't put the card back in the deck and shuffle them together, didn't put the marble back in the bag and mix it up, whatever, then I need to account for that when I use my multiplication rule. We're going to have ands and ors with these things, unions and intersections. That's why we talked about that. Every once in a while, we're going to have combinations or permutations involved with these things, which is why we talked about that. I already talked about binomial probabilities in one of the videos when I started to talk about combinations. And a good example of a binomial probability would be this idea of flipping a coin, because it only has 2 sides. See that? It's heads or tails. So that's a good example of something that's binomial, but the coin doesn't have to be fair. It doesn't have to always land on the heads half the time and the tails half the time. So I could figure out empirically by flipping the coin a whole bunch of times what the probability is that it lands on heads and what the probability is that it lands on tails. So these are all theoretical probabilities that I think, oh, because there's one side that's heads and one side's the tails, it should theoretically be 50-50. But if I find out that one side is actually heavier than the other side and it lands that side down more often, then these probabilities are going to change in actuality when I do an experiment and I figure out my empirical probabilities that way by doing experimentation. So your theoretical values and your actual values, or your empirical values, are probably going to differ from each other. Hopefully not by a lot, but it's possible that they're going to be different than what you expected. So we're going to have something that we're going to call expected value, which is this theoretical probability, expected value. And we're going to call that E, capital E of X. And that's going to be related to this idea of this X times this P of X. So that's the theoretical probability. We did not get into anything here with a raffle or a drawing or lottery of any kind. That's another type of classic probability problem. So I might do some worksheets on some classical probability problems that are raffles, as well as coins, dice, spinners, all those sorts of things where you know all the possible outcomes. We're not going to talk about questions right now, like, is it going to rain? Because there's so much uncertainty there in all the different events. It's not just a simple, is it going to rain, yes or no type question, like you would want it to be. So you have to do a lot with that forecasting. That's enough for right now, though. At the pre-calculus level, at the college algebra level, you should, once you know this stuff here, be ready to go into a introductory statistics or statistics 1 class and feel pretty comfortable with the concepts of counting, sets, subsets, unions and intersections, ands and ors. I said unions and intersections, so ors and ands, and this idea of probability, as well as different patterns that you need to recognize. And we talked about that with sequences, a little bit, but we want to be able to use patterns that we see to predict things that are going to happen in the future, or even in the past. And we do that with statistical models. So, all right, that's enough for right now. I look forward to seeing you in other videos in the future.